Thank you for coming to this webinar. We'll be talking about symbolic techniques, code generation, and we will be focusing on the FMI applications. Give you an outline of this webinar, some words regarding Maplesoft engineering solutions, our offering for engineering and analysis. We'll be talking about MapleSim, Maple, and our connectors specifically, and especially we're going to talk about the FMI connector. We'll be talking about the symbolic advantage, what does this mean, and how that becomes very, very important in code generation and FMI applications. I'm going to talk very briefly about FMI and how our tools generate FMUs, and we will be looking at some case studies. Okay, so Maplesoft provides engineering solutions, includes tools and expertise for solving engineering problems. These could include design validation, physics-based model, high-fidelity physics-based models for simulation, code generation for a variety of in-the-loop applications, creation of analysis design tools based on the physical models to explore what-if scenarios and to quickly get to the results by varying parameters and exploring the design space, and also other types of services such as model order reduction, and also venturing into the world of control and model predictive control. So looking at the software that are the base of our Maplesoft engineering solutions, we have Maple. It's a core flagship product of Maplesoft. It's a symbolic numeric environment for performing variety of analysis, calculation, math, and symbolic analysis, as I mentioned. Maple is a complete programming language that will allow you to create interactive worksheets to interact with your design and explore your design space. Maple provides the symbolic engine for MapleSim. MapleSim is our physical modeling environment, the multi-domain system-level environment to create models based on block diagrams. Each block provides the representation of a physical system and includes a number of equations. By bringing them to the modeling environment and connecting them together, one can easily and quickly create detailed and complex models representing variety of different physical domain from mechanical, rotational, thermal, magnetic, hydraulic environment and domains all together within the same environment. So MapleSim sits on top of Maple and uses the technology of symbolic computation of Maple. The same symbolic technology enables MapleSim to generate code from the models that get created with graphical means, the block diagram of different blocks, and from those components, equations are generated. That equations are manipulated with a symbolic technology, and then C code is generated from that. And we provide the fastest automatically generated model code because of the underlying expertise and the 30 years of development that has gone into Maple. The FMI connectivity will live within this third part. As I mentioned, symbolic will play a very central role in all of these three aspects. So considering a model, as I mentioned, a model within the physical modeling environment or system level modeling tools includes blocks that get connected together. As we see on the screen, we have here a multi-body model that includes joints and subsystem and forces and signals Once we have such a model created and tested and simulated, we can go on to generate code. But what is involved in the process of getting from a diagram, a graphical representation of blocks and connections, to actual code for simulation? So we start with a system diagram, of course, where we create our model. Then these type of approaches, the system level of physical modeling approaches, will inherently require symbolic manipulations. Why is that? Because these type of approaches eliminate the need for generation of equations and manipulation of equations by the user. The tool will take on that responsibility. For that, the symbolic parametric calculation of thousands upon thousands of equations are necessary. And we use Maple to perform these tasks. The second phase, which involves heavy symbolic computation as well, is the equation simplifications. Using a computer-generated equations for a block diagram will involve a lot of definitions, a lot of trivial equations that needs to be simplified, or you will have extra burden on your numerical analysis that is not necessary. On top of that, within those set of equations, you might have a number of them that are linearly dependent on each other. And if you can symbolically solve that, then you can also be more efficient. Other steps that can be done here when you have symbolic computation tool at your disposal is operations such as a zero multiplied by a large expression. And you can save on not evaluating the expression by evaluating the multiplication symbolically and substituting zero for that large expression. Matrix manipulations, trigonometric manipulations, all of that are in the realm of symbolic computation that we perform from the equation that generated from MapleSim inside the Maple engine. The next step for differential algebraic system is the process of index reduction. And this process involves performing symbolic differentiation of large systems. And that also requires an advanced and capable symbolic computation tool to perform those tasks. The next step, once the system is ready, is to causalize it. When you have groups of equations, those equations do not necessarily include the solving order. These are just a bunch of equations. The tool has to be able to order them and find the order of solution, basically causalize them, so that the equations can be solved one after the other to reach the final solution. At this point, the code generation happens. The C code is generated and optimized for maximum performance. And that is the code that is the basis of the numerical calculations that the tool itself performs. Also is the code that is available through our connectors, which I will talk about shortly. Those connectors get the C code, wrap them in different type of applications, including the functional markup interface as a functional markup unit, or FMU. So MapleSim includes a number of connectors for different types of platforms like DSpace, LabVIEW, and Simulink, and also FMI. So as I mentioned, because of the technology that we are using to generate those equations and optimize them and getting to the code, we create high fidelity models in MapleSim, but we create highly efficient optimized ANSI C code from them. And this ANSI C code, because of this multi-level optimization that goes through it, the symbolic optimization, would enable our users to perform real-time applications. So it is very important to be able to get from a high fidelity model, or at least keep as much fidelity as possible, and still be able to hit real time. This is also important for other applications that are not necessarily real time, like large optimization problems, that if you were able to reduce the time for a calculation of the entire simulation, then you can imagine an optimization that would involve hundreds and thousands of iteration would become feasible. So the functional mockup interface is a tool-independent standard, and it is aimed to enhance and streamline the process of model exchange between different tools. This is an open source standard, and it enables that the users from different tools that using different schemes, if they're using the FMI, they can interchange models and enhance the efficiency and output of their simulation work. It uses the C code, so it's natural that a software like MapleSim that provides C code can also embed that C code within the FMI standard and create FMUs that are also highly optimized. Taking a couple of slides from the FMI standard website, FMI was a project from 2008 to 2011 from MapleSoft. And after that, it has transferred to Modelica Association and continues its development through collaboration with from a number of tool vendors and OEMs around the world. So just going through some high-level motivation, we have models coming on from very different parts, and we want to integrate them all together. These are being using different simulation tools, and it's quite a challenge to migrate models from one model to an environment to another environment. Environments are usually specialized in different tasks, like one for electric motors, one specialized for hydraulics, one for multi-body. Bring them together is a challenge. Being able to have a standard, here the functional mockup interface standard, will enable the different tools to communicate with each other with ease and accuracy, and will enable the designers to have earlier access to design validations and increase efficiency and quality. Just some words regarding the history. As I mentioned, from 2008 to 2011 was the initial project that brought this FMI development forward. And after that, it is a project within the Modelica Association. The original effort was spearheaded by Daimler. At this time, more than 77 different tools provide FMI coverage in different forms. And this number, this staggering number, is increasing and is an indication of how ever increasing this standard is for the actual users throughout the world who are connecting different tools together to perform complex simulations. Both automotive, although where its start is, but also non-automotive organizations throughout Europe, Asia, and North America are now extensively using FMI. And we are going to now look at a few examples that we have been involved that showcases our involvement and how we play within this FMI environment. To start, looking at the block diagram model of a system, as we have seen before. This is a front suspension, a double wishbone, that is created with signals coming in and signal going out, and all within the block diagram. We have the dynamics of the system that is prepared for export, and this is from the MapleSim simulation environment. The process of export for FMI and other application of our generated code is very similar. We have templates within the Maple environment that enables and takes the users step by step through selecting the model, selecting the parameters, and it will do many tasks automatically, identifying inputs and outputs, options for the type of FMI, whether it's version 1, version 2, whether it is co-simulation or model exchange. Once you have done that, it will generate the code. This is the same code, as I mentioned, that is used for DSpace, Simulink, S-functions export with a separate wrapper that is according to the FMI standard. and then that can be integrated within the integration environment, and we will see some of the examples of that. Here's a first example. So as I mentioned, FMI will enable the integration of models from different tools. Here we have a manufacturer that uses MapleSim for hydraulics, as they have developed their different circuits in that environment, and uses MapleSim for detailed multi-body models, and then bring them together through their integration tool and combine them using the FMI standard. And they have found they have been very successful and made great use of this FMI standard to get results very quickly. Another example is in the domain of hybrid electric vehicles and also hardware in the loop testing. So the real time is an important feature here. The topic is the Powertrain. Being able to connect a hill-capable powertrain to a driving simulator, and obviously the need for real-time capability, and that is done through VICAR real-time. It was one of the aims of this study or this project was to control battery temperature throughout different drive cycles. So the powertrain model with the battery system had to be have enough fidelity to give reliable simulation of those effects within the bigger simulation. And the implementation environment in this case was the simulation workbench from Concurrent. Here we see a sample model that includes the parts that we just talked about. We have at the end here a representation of vehicle, and this is done here just to test the model within the simulation environment before exporting. It's also important that the simulation environment will be capable of testing the pieces and give confidence before exporting the FMU to integration environment. The model incorporates the mean value engine, power electronics, and thermal effects, the battery system, and electric motor. So the system that incorporate the powertrain, the electrical system, and battery was isolated and causalized, and the FMU was generated from it. So it is in some interesting numbers, 12 microseconds for running the mean value engine, adding the conventional powertrain up to 52, and the full HEV powertrain with cooling 94 microseconds. And we have the specs of the machine as well. And that achievement enabled the simulation to hit a real-time target. And here we see pictures of the driving simulator that under the hood could run that hybrid electric powertrain. The other example here is a case study. Case study number 3 is with QTronic. So here again we have another vehicle application, this time for validation of the ECUs. For that reason, having a high fidelity vehicle model was important that is also capable of running in real time. So the outcome was virtual prototyping process and supporting tool chain that would eliminate some of the non-compliance tests, like non-compliances that could potentially occur very, very early in the design. The model was created in our environment, MapleSim, including the vehicle transmission engine and shifting logic and torque converter and other parts within the powertrain system. The FMI connector was used from Maple to generate the code, and it was integrated in QTronic Silver for the real-time testing. which resulted in significant cost and time reductions in the prototyping stages. Here we see a picture of the model, and as it appears as implemented within the silver environment, working together with the virtual ECU, and some results of the engine RPM as shifting occurs. Another example, this time is also automotive example, but with IPG Carmaker. The project was for a power steering system, being able to generate a high fidelity power steering and with power assist steering system into the bigger simulation environment of the full vehicle. So the power steering was created in MapleSim, and the code was generated. The idea was to make it fast enough that the whole thing would hit the real-time target. So the modeling was done within MapleSim, and the FMUs were generated from MapleSim, and the test showed that was able to run 7 times faster than real time, which was a significant improvement from their previous iteration using other software. Here is a view of a sample steering. Well, actually, this is the full chassis, and we see the steering subsystem that is connected to it. And this part was isolated, causalized, and exported as an FMU. And the Carmaker environment was used to implement that into the bigger system. And here is a sample of the simulation of the system, going through a number of maneuvers. And this is another view of the results and some plots of the outcome of various variables in the model. So being able to, this is a real-time simulation, and it's very important that the pieces added are efficient enough that does not cause overrun on time budgets. Here we look at another example. This time is the FMUs from MapleSim integrated in the DSpace SCALEXIO platform. We see a transmission system that was the target of this work. This transmission system is done through by using the components from a library that we have developed here at Maplesoft called the Driveline Component Library. Is a collection of components written in Modelica that enables the generation of a variety of powertrain and driveline components with ease. So these components were used in this transmission, and that part was exported with the appropriate inputs and outputs for different types of actuation measurements, and for the measurements of speeds and actuation for clutches and brakes within the transmission, and exported to the SCALEXIO platform. Here we see some of the results. We were able to achieve an average full vehicle model execution time of 300 microseconds, with a small percentage of that being the transmission system that was provided by MapleSim. Another example is LABCAR from ETAS. Here we have also the target was hardware in the loop and real-time simulation. The vehicle models the plant was coming from MapleSim again, and using FMI connector to generate the FMUs. This vehicle model again was a hybrid electric vehicle, including the powertrain, electric motors, power electronics, and batteries. Some results and numbers. There were tests by using the in Simulink, using the Simulink solver and also the MapleSim. So we see that 20 microsecond for MapleSim model, 320 microsecond for the Simulink model. Runtime violations, an important number. There were only 2 during the initialization, which on the other hand, the Simulink one had too many. Some overview. We used the implicit solver, embedded solver from MapleSim. The implicit solver is very powerful for systems with high stiffness to be used. We provide a number of different solvers, including the implicit solver, and that was compared against the OD14X from Simulink, and the results are given, which, as I mentioned, there were only 2 violations of the real-time during the initialization phase, none during the actual simulation, which was a huge achievement. In general, the MapleSim implementation increased the speed by a factor of 15, which it is very consistent with what we always see in different applications that we do for our customers, that up to 10 and beyond is the speed up factor that we see when we go head to head and comparing same models that came from different environments. And that's an indication of how the symbolic optimization that we put into generating the code from MapleSim can benefit this type of application, as I mentioned, whether it's real-time or just a simulation optimization. So within our scope of generating code, we excel at generating the fastest automatically generated C code from a system-level model. That plays very well with the FMI standard that provides a standard for model exchange and code simulation between different tools. So our technology for generating the fast code enables a large number of users that are to be able to incorporate our very efficient code within a bigger set of simulations. The symbolic technology, as I talked about it, comes into play in a number of different from number of different fronts, and the final outcome of that, as far as the code generation is concerned, is a high fidelity model that is also very efficient. And also there are other aspects that we saw within the bigger engineering solution, is to use that symbolic for doing further analysis and modeling. So, and that is where the Maplesoft engineering solutions comes into play, which together with the tools that we provide will help you reduce the development risk, produce better products, and get to market faster.